Hey, howdy everyone. We're going to try something new today. I have a set of in-class demonstrations or examples that I'm going to do in front of you, and I'm going to do them both in R and Excel. The purpose is we'll do it in Excel by hand to show you exactly how it gets done, but in R we'll take advantage of the statistical packages, which are basically a one-line command to get the job done. And I'm going to show you basically why I am in love with R. I like Python too. I'm just saying I just find R so easy to get the job done, and a lot of statistical things that we have to do at work. Plus R is, very easy to work with, and I'll show you why. And I'll show you, we'll do some more Python. We'll do Python later on too, don't worry. But so first of all, we're going to do a confidence interval and hypothesis testing in R. We're going to check the examples by hand in Excel. So I'm going to walk through this with you. So first of all, I'm going to need you to make a working directory on your hard drive and then copy these files into that directory. We have our R code, which is lecture 7, confidence interval hypothesis example R. And then we have the Excel worked out by hand here. And we have a data file that we're going to work with. The data file has two sets of porosity measures from the subsurface. Once you've done that, let's go ahead and open RStudio on your laptop. And once you've done that, go to File, Open File, and select the R code, open it up. And also, while you're at it, open up Lecture 7, Confidence Interval Hypothesis Example R in Excel. So, if you do that, this is what you will see on the R side. The RStudio program is opened up. If you have never worked with an IDE before, which is an integrated development environment, then you're in for a treat. This is exactly what RStudio is, and I find it very nice. It does all of the package management for you. It does the, you can run code step by step. You can look at outputs. You can look at figures or images directly in it. You can look at all of your variables and all your objects you're creating. So I really like RStudio. So when you open it up, you're going to be able to see that file is up here. So you can go to File, Open File, and you'll be able to open up the code. And we'll do that together, but I'm just showing you around the interface right now. When that opens up, now you're going to see the window look like this. You're going to see the code right here. And the first thing you'll notice, a lot of the code is green. There are the hashtags there, which mean that those are comments. I put those in there because I wanted you guys to be able to read and to interpret what's going on. If I just gave you a pile of code with no comments, it'd be harder to understand. So we comment our code to be able to understand the code. We have the output down here. As we run it line by line, you'll see output appear down here. You can look at that. You can see the various things that are going on. And as we run the code, we're going to be creating variables and objects, and we can expand and look at those objects. And at times, we can use this for a lot of different things down here. We can look at the current directory that we're working in. We can look at the plots that we're generating. If we're generating plots, we can look at the packages we've loaded. And there's also help files and so forth are available there. So with that, let's go ahead and get started. Now I have opened up my R here, RStudio, and I've opened up that specific file that I mentioned. And so this is just the beginning. I ran something. Okay. I did actually run a couple lines of code. What I will do is I'll go to Session, Clear Workspace. I want to make it fair. I'm going to be just like you guys. I'm going to start right at the beginning. I don't want to start already running. And over on this side, you can see I have the Excel open, and I have it open to the very first sheet, which is my confidence interval. And what you'll notice immediately is that I have the data set that we will be loading in R. It's there. You'll notice it's only got 2 digits in it. When we load in R, it'll also look just like this. I'll show you. In fact, why don't we get that far? Why don't we go ahead and load it in R? First thing you want to do is set your working directory. On my working directory, I'm just working directly on C, and I assigned a subdirectory or folder which has the name of the course PG337. So the cool thing about R is that any time, just in case you haven't gotten this far, File, Open File, navigate to the file with the R code loaded up. That's what you needed to do to get to here, just in case you're stuck. Okay. So we'll The cool thing about R, as I was saying before I interrupted myself, was that you can run lines line by line. So anyway, I could select this line right here. This button right here is the run button. And if I hit run, it'll skip through all of this because these are comments. And then it'll run the very first line of code. And if we look down here, everything is in blue. We're good. It ran. So we can assume right now that our working directory, in fact, is this directory right here. We didn't get an error. Next line of code is really, really easy to work with. What it's going to do is take and read that comma delimited file with that name in our working directory. It'll default and go to your working directory. And it will turn it into an object called myData. And that myData, in fact, is a data frame. And so let's go ahead and load it. So I just put the cursor there and run it. Now, you could have just kept hitting run, 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 run. It would run every step and we'd be fine. But as I'm talking around, pointing around, and so forth, just acknowledge that if I put my cursor here and ran again, I would repeat that command again. Wouldn't have any consequence. It could potentially, depending on what you're doing, how complicated your workflows are, you may not want to willy-nilly just be running lines of code. You probably want to go in sequence. In addition, don't skip any lines. I have that problem all the time when I demo this or work with the students in class. They'll come to me and say, I ran this and there's an error. It can't find a variable. It can't find an object. And I ask them, did you run it from the beginning? And they didn't. You've got to actually run. In fact, think about it this way. Until you run this command, set the current working directory, your computer, this instance, doesn't know that that's your working directory. The computer doesn't know until you run it. You haven't created it. You haven't done it. You haven't altered it. So you have to actually run each line of code. And I'll give you a perfect example right here. Look, we have no objects. Nothing's been loaded. We're going to run that command I mentioned before where we load our comma delimited file directly into a myData data frame. It's called myData. That's how we've named it, myData. And watch this. When we run that, oh, I didn't click right there. Okay, sorry. When we go ahead and run that, what I actually did was I selected the space, not the line, and so I ran a space. Yeah, you can run subsets and so forth by selecting. I meant to just put the cursor down. So when I run that line, what happens is you'll notice that I now have under data, myData. And it's a data frame. In fact, you can hover on it and you see it says data frame. It tells you that there's 12 objects and that there's 2 variables did I say 12? 20 objects, 2 variables of them, right? So the cool thing, I love this about R. I can just double click here and I can visualize exactly what's in that data frame. I can see what's in it. So anytime you have an object, you can click on it, try to find out what are the parts of that object. And so we have the object. We have the data frame now that we can work with. So I'll close that up. I go back to our code. And so there's a lot of very helpful commands specifically with data frames. Now, if you're interested in learning about working with data frames, I have a tutorial or workflow with data frames in Python. I think I also have one in R. I'll check. If I don't, I should put one out there. But I'm pretty sure I've done that. Okay. If not, there's tons of really good tutorials online. So here's something you can do with a data frame. Head. That'll give you the first 7 lines, the first 6 data entries, plus the titles of the variables. And so 1 through 6, we know there's 20. It's not all of them. But it just shows you, if you've loaded data and you just want to preview it, and let's say it's 100,000 samples, you can't look at them all. It would just run forever. So head gives you a chance to take a quick look and see what in fact you've loaded. Now there's tons of different routines to do summary statistics in R. So summary is built right in to a data frame, and you go ahead and look at that. You get the min, the max, the quartiles, the median, the P50, the median, the mean, and so forth. So very useful summary statistics. You want to QC your data. I don't have any negative porosities. I don't have porosities greater than, say, 30% or 40%, which would start to become unrealistic, and so forth. So this is pretty useful too. Now, there are a lot of different summary statistics, and I got a little bit, carried away. But if this is the first time you're running this, uncomment this line right here and run this line to install that package. I've already done that. Now, it's not a big deal. I could run it again, and it gives me a thing saying, okay, you want to update it? Do you want to restart? I'm just going to say no, and it'll try to go ahead, and it'll install it, and then I can go ahead and just, when I use the library command, I'm saying, okay, this package has been installed. I want to use that. As soon as you use library, you say, okay, in the rest of the code, whenever I call for a command, go ahead and look in that package too. I'm using that package. So you're letting everything know you're doing that. And so if you run this describe that's part of this HMISC package, or H miscellaneous, you'll get a really nice set of, for different thresholds or bins, you get the frequency. So effectively, it's giving you a binned histogram plus the proportion, which would be like a bin PDF, right? So it's nice, and then it gives you a variety of different statistics and so forth. It tells you, it does a little data QC. It tells you if you have null values or anything missing, and so forth. So pretty useful stuff. Now I'll put one more in. Once again, uncomment this line if you haven't done this before. I have, so I'm not going to try to reinstall that package. And so I include the package by saying library in the name of the package. And I'll go ahead and run that. And this will give me a whole lot of statistical descriptions here. Now, of course, we can readjust the window here so we can see everything. It tells you about if you have null values. It tells you if you have not a number of values. It tells you about the min and the max, the range. It gives you the median. It also, look at this, you get the CI, the confidence interval for the mean at the 95% confidence level. And what this number is, it's going to be the half width of that. And so you get so basically it's going to be your t-score multiplied by your standard error, the half width, right? That you do the plus and minus on the mean to get the upper and lower bound. So you get all of that just automatically by using this command. So, and variance, standard deviation, sample standard deviation, so forth. So summary statistics. So now let's go ahead and we'll demonstrate in our how would I calculate a confidence interval. Now we've talked about this a bunch of times in the notes. We've talked about the equations where we're going to assign an alpha level. The confidence level is just 1 minus the alpha level. And so what we're going to need in order to proceed is we need the sample standard deviation, we need the sample mean, and we need the number of samples. And so let's just demonstrate this on X1. Now something very cool about R, I have a data frame called my data. But if I just want to access variable X1, or in fact if you have any type of object and you just want to access that one thing in it, you're always free to use this dollar symbol and then specify. And so you'll find there's even nice autocomplete going on here. If I type a dollar symbol after my data, it'll show me what I can access. And I totally dig that. That's very helpful to get these kind of tooltips, right? Or not tooltips, more kind of like autocomplete or assist, right? So and we can calculate these commands here are built-in. SD is sample standard deviation. Mean is the mean, and they can work with any vector of numbers, which is exactly what we get when we put the dollar symbol X1. It returns that vector of values. We get n row will tell us how many samples there are in our data frame. In our data frame, we would expect the same number of samples for each variable in the data table. That makes sense. Most of our data sets, that's the way we are. And so then we calculate the standard error. We know the standard error is just the sample standard deviation divided by the square root of n. And so let's go ahead and step through these lines of code. Alpha is set. Now notice as soon as we set alpha, look what happened. We now have a value for alpha. So you can track what variables have been set. What are you working with? Let's run it again. S1 is now calculated. We now have the sample standard deviation available to us. So at any time, now we've done this in Excel, so let's check ourselves as we go. For X1, the sample standard deviation is 0.0278. So we're good. That's working for us. So we're good. We're getting the right numbers back. Let's go ahead and run and calculate the mean. So M1 is going to be equal to the mean. You run that and you get an M1 variable, and that's equal to 0.1645. And if you go over here and you check out this value here, you've got 0.16, and I'm missing a couple decimal points, but that's fine. They're there. The n is now the number of rows. If we do that, we should get 20. It puts it 20L because that's indicating that it's a long integer. Don't worry about that you can use it in math. You can do whatever you want with it. It's 20. It's just telling you what kind of variable it is. And so the standard error is simply going to be S1, or the standard deviation of that data set, sample standard deviation, divided by the square root of n. And we go ahead and run that, and we get 0.00621. And we can come over here, and we can check that out, and we've got the value right here. Our standard error is right there. Now we're going to need a t-score. And so we're going to look up from the t distribution. Qt does that for us. And the cool thing is we can do a C brackets lower and upper percentiles, the cumulative percentiles we want. Every time you do that in R, you're saying make an array which just has those two values together and run them both through the command at the same time. And so now the output will be an array with both of the t-score negative and positive at the same time. And so that's kind of cool. You can do everything at once. And degrees of freedom, of course, we know it's n minus 1. So we got that there. And we run it and look what happened. We get t-score, the negative 1 for the 2.5 percentile and the positive 1 for the 97.5 percentile. And so we can go ahead and look at what we have going on over on the other side here. And so we see that our statistic right here for our t-score was exactly 2.09, and we're going to use that plus and minus. So so far so good. We got exactly the same thing as we have in Excel. And so our final step, we're going to take the mean value, the sample mean, and we want plus or minus the t-score times the standard error. And we know that our t-score was already an array with the negative and the positive side. So if we run this, we're going to get the confidence interval all in one step. We don't have to run lower and upper bound. And we run that. There it is. So there we go. We got the confidence interval at the 95% confidence level shown right here. It indicates where our mean was 16.5%. We go from 15.1 to 17.8. If you come over here and take a look at the Excel, this is exactly what we got on the Excel side. So for completeness, you could go ahead and repeat this exercise for the X2 data set or the second well porosity values, if that's of interest to you. Let's go ahead and try some hypothesis testing. So let's go to the Excel side and look at how we would do that. And so we talked about in class how we would do a difference of means calculation. We got two different types we can use. We got the pooled variant where we're basically assuming that the variances are equal or close enough. And then we got the unequal variances, the Welchs Ttest, where we're going to account for the fact that the variances are not the same. So let's go ahead and do the general pooled approach first. Remember, it has a much simpler degrees of freedom. The overall calculation is pretty simple. Now we can go through the Excel and demonstrate to you that this is how you would do it, that the mean, the sample standard deviation, and the count. And we've done that for each data set. If I click on it, you can see, in fact, it is for that data set. And this one's been done for the second data set. So far, so good. The measure is just going to be equal to, the measure is just going to be equal to the mean of the first one, subtract the mean of the second one, and so we get a negative 0.04. The standard error, recall the equation where we have the square root 1 over the number of samples in the first one plus 1 over the number of samples in the second one. And then we're basically, it's like we're weighting the standard deviations of each one of them by number of samples. And so that equation, of course, I could pull up the notes right here. I should be able to get to it pretty quickly. Let's see. It is, there it is right there. So we have the calculation for the t-statistic, the metric, divided by the standard error, and there's the equation. And if you could walk through this, you'll see that that's exactly, this command right here is exactly this equation. And then what we're going to do, and so we got the standard error, we got the measure, we just have to take the measure divided by the standard error, and we get the t-statistic. And that's where we get negative 2.98. The t-critical was calculated by using this equation right here. Of course, we got to account for the fact that we have two tails. So we'll take alpha and divide by 2, or we can use the Excel command with two tails and just put alpha in. So we put alpha of 0.05 there, and the degrees of freedom is just n1 plus n2 minus 2. And so if we do that, we get our t-critical, we do our test, and we find out that we're outside of that interval. Therefore, we are going to reject our null hypothesis. Our null hypothesis being that the means were equal to each other, and we'll say that we can show that they are statistically significantly different from each other. Now, of course, we may want to calculate the p-value. That's pretty useful. All you got to do that is take your t-statistic, put it back into t-distribution, and calculate the associated probability, cumulative probability. Now, I showed 2 times that right here, because of the fact that the p-value in R is shown as the two-tail, the area or the probability of outside of the positive or the negative of that t-statistic, which effectively would be the alpha value at which you would first reject that, that you would first fail to reject that hypothesis. It's the threshold at which you reject or accept. And so what are we seeing? It's 0.5%. So in other words, we were testing at 5%. We're not even close to failing to reject. We'd have to, in fact, be testing with an alpha value of 0.5, about 0.5 before we would even fail to reject. So you can see this is clearly, the means are not the same as each other. Okay, so I've shown the equation. We walk through the Excel. I'll keep the Excel up, and let's just go ahead and I'll show you why I love R so much. Okay, so let's go ahead and we'll run this line of code right here. This is going to be our t-test, assuming pooled variances. It's going to give us all of the output down below. So what happened? We ran that one line. It got a t-statistic of negative 2.98. We look over here. That is, in fact, what we got for our t-statistic. The degrees of freedom are reported. We know that that's what we used here, that in fact we had n1 plus n2 minus 2, which was 40 minus 2. And so we're good there. And the p-value, as I warned you, is going to be reported as 2 times the p-value we got from the cumulative, because it's the alpha level at which you would imminently fail to reject, right? And so it's accounting for the two tails at that point. And so you'll see when I multiply by 2, I get the same thing. So really all of the samples, this all checks out. And with one line of code, we have just conducted our pooled variance t-test for difference of means. Okay, so that was good. That was useful. So what about the other t-test, Welchs Ttest? And so Welchs Ttest is you don't assume that the variances are equal. You can unequal variances. And we know that the measure is going to be the same as before. The standard error is going to be a simpler calculation. Let me just pull that up on a slide right now. I should have that. There it is. So the t-statistic is shown like here. The measure is the same. The standard error is actually very, very simple. But hey, there's no free lunch. Your standard error calculation is very simple. But when you go to calculate the t-critical, you have to account the degrees of freedom become actually pretty complicated. You have to use this equation right here. Okay, so that's what we're going to do. We did it here in Excel. You could go through the sheet if you download it, and you can confirm that we've got this right. If not, let me know. We got the U value, which was the one shown right up here. We've got the degrees of freedom, which I broke up to have the denominator and the numerator, and then to divide them because it was just so much. I wanted to kind of break it up. And so we get our degrees of freedom. Interesting, they're not 38, they're 31.5, which is kind of interesting, right? The t-statistic is shown right here. It's the same as it's really close to the one we had before, but the t-critical is different because we have a different degrees of freedom now. Okay, so once again, if we look at our test, we're outside of that interval. So we're going to, once again, we're going to reject the null hypothesis, and we're going to accept that, oh shucks, no. We're going to reject the null hypothesis, and we're going to accept that in fact, that the means of x1 and x2 are statistically significantly different from each other. And we can look up the p-value just like we did before. And so we're just going to take the t-statistic, get it from the student t-distribution, cumulative, and we're going to use the degrees of freedom that we calculated, 31.5, to be consistent. And so we've done everything now in Excel. So that took some time. I had to write all that, and that was kind of a lot of effort and so forth. So let's go ahead and run the same thing in R. So watch this. That's it. So we got our t-statistic, negative 2.98, negative 2.98. You could round it up, and 2.981. Degrees of freedom, 31.49. That's good too. The p-value, 0.55%. We're good. We look really good there. And we are going to have the same thing where we reject the null hypothesis. The means are not equal to each other. Okay? So that's good. So basically, that's all we had to do. Now let's take a look. One more test. Let's look at the F statistic, specifically to test the difference in variances. And so we'll take our two data sets. We'll go ahead and we'll apply the test. Now if we go back to the slides that we had available to us, the F-test is actually quite a bit more straightforward than what we had to do with the T-test for difference in means. The F-test is explained right here in the notes. The null hypothesis of the variances are equal to the ratio of the variances equal to 1. Therefore, they're very similar to each other. We will order them. And if we order them, we'll say that the variance of the one on the top must be greater than the variance of the one below. And so now we're going to test to see whether or not, in fact, what this should be right here is that it should be, the alternative hypothesis is that this is in fact greater than 1, that the ratio is greater than 1 because we're forcing by the ordering. We're not concerned with it being less than or just not equal to. We're saying that it must be statistically significantly greater than 1. So we go ahead and we can calculate the F statistic by taking the variance, the greater variance, putting over the lesser variance. This is our constraint. That's our F statistic. And we look up F critical by taking the data set with the larger variance. The degrees of freedom are n, number of samples in that data set minus 1. We have 2 degrees of freedom, 2 data sets here in this test. And so we'll take the second data set with the lower variance, and we'll take n minus 1 for the number of data, and we'll put the significance level. This is a one-tail test, so we don't have to do any of that dividing by 2 or anything like that. So let's go ahead and we'll look at the result from that test. We got our 2 data sets. Our F statistic is calculated by taking the variance that's larger over the variance that's smaller. I used min and max commands to make sure that happened. And then I'm going to go ahead and calculate my F critical. We're going to work with right tails. What does it mean if we work with right tail? It means I can put the alpha value directly in the equation, and inside of Excel it'll say, well, you said you're testing at 5%, but on the right tail, that's technically the 95th percentile. That's the value in fact you want, and Excel will take care of that for you. We got the number of samples in data set 1 and 2 minus as the 2 different degrees of freedom. And if we do that, we get F critical of 2.17. And so if we check our statistic, once again, we'll find out that we are greater than the F critical. Therefore, we are going to reject and show that we reject the null hypothesis. The variances are statistically significantly different from each other. And we can go ahead and calculate the p-value. The p-value is calculated by just going to our F distribution and using that specific F statistic that we got, and with the right degrees of freedom, and it'll look up the associated p-value for us. So let's go ahead and I'll show you once again why I love R. You saw all the stuff I had to put in Excel to make that happen. The F-test, we've got our 2 data sets, x2, x1. We ordered them so that the one with the greater variance is going to be first, and then we put the constraint that we want to only test for the case that's greater than. Then we have the same test that we did in Excel, and we can go ahead and run it. We get all of the output, and we're going to find that our F statistic is 2.667, rounds up to 2.67 over here in Excel. We got the degrees of freedom for both the numerator and the denominator. The x2 and the x1 are 19 and 19. That's fine too. And we get our p-value of 1.9%. That's exactly the same p-value we got. Most importantly, we will see that we have rejected the null hypothesis. The variance is greater than 1, and we know that by the p-value being less than 5%. That makes sense. We've rejected. And it even calculates the ratio of the 2, which is the F statistic we used. That's right there. So you see, with one line of code in R, we just ran exactly the same thing that took quite a few steps within Excel, or if we used a calculator. Now the other thing too, let me just show you one more thing and then I'm going to finish, is that you could have at any point said, okay, T-test, this would be pooled, and you say equal, pooled, okay? And what would happen is instead of writing the output to the screen down there, it would have actually created an object that would have all of those parameters in it. So at any point you could store that. You could keep all of these various different outputs up here in the objects. You could at any point, this is kind of cool too, once you've created that object, I could then decide to grab a piece of that object. tstat is equal to ttest pooled. Now, I misspelled that again, excuse me. And then you can go ahead and do $, and you'll see immediately that all of those objects, all of those sub-objects or variables or parts of the object are available to you. And so I could do that. And if I run that, what you'll see is that I've actually grabbed the t-statistic directly out. And so if I want to use it in subsequent calculations, I could grab that out and work with it. So once again, using that $. There's so much to learn about what to do with R. We haven't even done any plots or anything, but this was a nice introduction. And I think it demonstrated the fact that R does provide a very nice, well-contained, easy to work with approach to be able to do things that will take a lot of steps in a lot of other software. Also, R is very well documented. You could always look up these commands and get to their docs, and you'd find out that everything's explained about what are the various inputs, what are the variants you can run, and examples are provided. So I really do appreciate R. All right, I hope this was helpful. All right, that's it.